Everyone, welcome back. So this time we're going to talk about rotation about a fixed axis. Okay, rotation about a fixed axis. Now, when a body rotates about a fixed axis, any of the points P in that body, they're on a circular path. Okay, a circular path that spins around in a plane perpendicular to that axis. So we can figure out what point P is simply by knowing what the angle it is, where it is. Now that change in angular position, d theta, is called the angular displacement. And it's going to have either units of radians or revolutions, where one revolution is 2 pi radians, or that's going to equal 360 degrees, but you never use degrees, always radians or revolutions. So our angular velocity and angular acceleration are going to be simply taking the derivatives of that. So first, angular velocity, I take my derivative. I get that angular velocity is simply d theta dt. How much is the angle changing with time? It's usually measured in radians per second. And then my second derivative, d squared theta dt squared, is going to be equal to my how much my angular velocity is changing with time. Or if I don't know that, I can use the chain rule to say, okay, it's equal to my angular velocity, and then how much my angular velocity changes per angle. This might be helpful sometimes. The chain rule will be beneficial to you. And in both these cases, we're saying that counterclockwise is positive, which has been a common thread through all of our past sections. Now, if the angular acceleration of the body is constant, you're going to run into some equations which should look very, very, very familiar. And I'm hoping that these look very, very familiar to you. If they don't, let me try changing a couple of variables. Let's turn that into a v and that into an a. We're going to turn this into an s, this into a v, that into an a. V, v, a, s, s. Does it look a little bit familiar now? Hopefully, because those are our kinematic equations. Our projectile equations, in fact. So yes, you can use very, very similar ones when we have constant acceleration. Okay? And all the knots right there, those are the initial values. And like I said, these are very similar to the rectilinear motion equations we had much earlier. So don't forget these. It keeps on coming back. If you mastered it once, you're going to have an easy time now. Okay. Now, what is the velocity of point P? Not the angular velocity, but just the regular old velocity. Just don't call it old, and to its face at least. Might get upset by that. Well, it's not too bad. What you all probably remember or know is that if you're swinging a ball around on a string, the further away it is from the center, the faster the ball goes as you rotate it around. And so, if we're trying to figure out how far it's gone, well, it's gone 2 pi r, per rotation. 2 pi r per rotation. And so the bigger the radius, the faster the velocity. Bigger the radius, the faster the velocity. Now, for us, what that means is simply saying, okay, it's going to be my angular velocity crossed with the position vector to that particular point. Angular velocity crossed with the position vector of that point. And we're using the right-hand rule to determine the direction. Okay? This is a fairly simple equation, and as long as your position vector is perpendicular, which it always should be, to the velocity that you care about, you're good. Like, there's not really anything you have to worry about. Your angular velocity is coming out of the page. You have this position vector. All is good. And when you take those, you're going to find that your velocity is going that direction. Now, it's going that direction over here, but we'll worry about that at the moment. What about the acceleration of that point? Well, guess what? You're going to have the normal and a tangential component, which you should be familiar with. We ran into this quite a while ago. So we're going to have that be angular velocity squared times r, and equal to our angular acceleration times r. Okay? And do not get these confused. Angular acceleration and tangential acceleration, different things. Angular velocity and your regular velocity, different things. If you see angular, it's different. Okay? It's different. You can kind of think of these as like straight line kind of things, and these as curved line. But do whatever you need to so you can keep those separate. Now, the tangential component represents how much the velocity is changing in magnitude. So is it going faster and faster as it goes around? Now it's this fast. Now it's this fast. Now it's this fast. It's accelerating. And it's always directed tangent to the path of motion. The normal component is what is causing it to turn around in this circle. And obviously, the faster I'm going, the faster you're going to have to turn, so the greater your normal acceleration will be. So, if we want to, we can then develop equations for this. So we know our acceleration is going to be equal to our change in velocity with time, which is equal to our position vector times the change in angular velocity with respect to time, plus my angular velocity times the change in my position vector with respect to time. I said times here, that is a cross product. So please don't get confused by me saying times. It should be cross. And so we set it up like this, and then we simplify a little bit, and what do we get? Well, we get a very, very similar equation to what we had earlier, which is simply saying that our acceleration is going to be equal to our tangential plus our normal components. And note that we've gone from a vector here to a scalar right here because of an identity with this. And as always, you can find the magnitude using this equation. Okay, so let's talk about the procedure and then we'll finish it up here. So first off, establish a sign convention along the axis of rotation. What's going to be positive, what's going to be negative. If you know a relation between any two variables like acceleration and angular velocity or angular displacement, you can figure out all of the rest using these equations to take some derivatives or take some integrals. If alpha is constant, so if your angular acceleration is constant, then you can use your constant angular acceleration equations, which are like those projectile motion equations. Then finally, figure out the motion of a point. You can use these equations to relate everything to our regular velocity and acceleration. Or if you want to, you can use the vector form, but I really like going with scalar form if I can. So I believe that's everything. Yes, we're going on to an example. So thank you for listening. I hope this helps you, and I'll see you all next time. Bye-bye.